Welcome back everyone to a session on Unix programming. This will be the last video lecture on module 4. Here we'll be covering the topics of shared memory and also client and server properties. So as seen in the previous lecture videos, IPC mechanisms, we have learned how the message queues and semaphore works, right? So that is used as a method for a process to communicate with each other, right? And in today's session we will look into another IPC technique, that is shared memory. So as the name suggests, shared memory allows two or more processes to share a given region of memory. So in this given region of memory, multiple processes will try to communicate. In other words, it will one process will write something onto the shared memory, and the other process will read the content what is written by one process in that shared memory. So using that shared memory, the processes will communicate with each other, and this will be the fastest form of IPC when compared to the previous one, because the data does not need to be copied between the client and the server. And the only trick or the headache that we need to consider while using shared memory is to synchronize the access to a given shared region among multiple processes. Uh, for example, if the server is placing a data into a shared memory region, the client shouldn't try to access the data until the server is done, right? So this is the headache what we need to address, and this can be easily done by using the concept of semaphores, which we have already seen in the previous videos. Okay, and yeah, that's the point. Synchronizing access to the memory is required. Okay, and for a shared memory, the kernel maintains a structure with at least following members for each shared memory segment. Okay, so this is the structure that is maintained by the kernel as as relatable to the previous IPC techniques, message queues and semaphores. Even there, the kernel maintains a structure, right? So the name of the structure is shared memory ID underscore data structure. Okay, and these are the various members. So this is something what we have already seen. So this is with respect to the permission and accessibility to the shared memory. Okay, which process can access, and what is the mode of access. So all this is defined in a general another structure, IPC permission. Okay, okay. So then about, yeah, shared memory segment size. So obviously this will represent the size of the segment in bytes. Okay, shared memory LPID. L stands for last PID. So this is the PID of the last process that makes use of the function sh shared memory operations, which we will be looking in very soon in the next slides. Okay, then CPID. So this will be the PID of the creator. Then shared memory attach. So this will be the number of current attaches to the shared memory. Okay, and a time represents the last attach time. So last attach time in the sense, see, the shared memory need to be accessed to the address space of one of the processes, right? So this time represent at which at what time the shared memory is attached to the address space of the process. Okay, so this will be the detached time, when the shared memory is detached from the processes address space. Okay, and C time represents the last change time. Okay, so all these three are with respect to time. Okay, so this is about the structure that is maintained by the kernel for a shared memory IPC method. Now let us look into the various functions that are used with respect to shared memory. And the first function what we normally use is shared memory get. Okay, SHM get, and this is used to obtain the shared memory identifier. the concept what we have already seen with respect to message queues and semaphores. First, we need to get the identifier for the IPC structure. So that is done with respect to shared memory by using this particular function shm get. And let us now see the syntax of this. Okay, so obviously it will return a integer type, that which is nothing but the identifier, and uh, these are the parameters that are passed. So we have to pass the key. We have already seen how the key is generated and how the key is converted to an identifier in our previous lecture video. Okay, and these are the other two parameters. Let us discuss about this a bit later. Okay, and it will return shared memory ID if the function is successful, and it will return -1 on error. Okay, and when a shared memory is successful, the following members of SHMID data structures are initialized. Okay, so these are the some of the members of SHMID data structure what we have seen in the previous slide. So these are the structures that will be initialized. The IPC permission structure, okay, it is initialized, and the mode member of the structure is set to the corresponding bits of the flag that is mentioned here. Okay, so obviously permission need to be assigned, right? And the mode value, the mode in the sense the read write permission and read only permissions, all this for different processes will be set based on the mode value, and what value the mode will get, that is based on the flag value what we pass as a third argument to this particular function. Okay, yeah, and the last PID, the number of attachment, uh, attachment time, detachment time, all is set to 0. So this is when the when the segment is created. Okay, and change time is set to the current time when the function was called, and the size of the segment is set to the size that is requested as a second parameter. So size of the shared memory is nothing but whatever that is requested, and it is passed as a value as a second parameter to the SHM get function. Okay. So this is about shared memory get function, which is used to get a shared memory identifier, and these are the changes that happens in SHMID data structure when this function is successful. Okay, so and these are the values that are initialized. So this is about shared memory get function. With the SHM get function, it is possible for us to create a new segment or shared memory, and it's also possible with the same SHM get function to reference the existing already created shared memory. Now let us see another function, SHM CTL function. So with this one can perform multiple operations on shared memory. Okay, and the function syntax goes like this. Okay, so as you can see, the return function is integer, so it will return 0 if successful and -1 on error. And these are the various parameters. So SHMID is something that we obtain using the SHM get function, and to perform operation on the shared memory, obviously we need to identify it, right? So that is done by using the ID what we have obtained with the previous function SHM get. Okay, and command specifies what kind of operation what we want to perform on the shared memory. Okay, so this will answer on which shared memory I have to perform operations. This will command, second parameter will answer what operation I want to perform on the shared memory. Okay, and let us see about this later. Okay, so now let us see the various operation that I can perform using SHM control function on the shared memory. Okay, so these are the various operations. Okay, yeah, so let us see each one of these. Okay, the first one, IPC stat, it is used to fetch the SHMID data structure for this segment and storing it in the structure pointed by the buffer. Okay, so it will fetch the data structure for this particular memory segment, and it will store in a structure that is specified in the buffer, that is the third parameter, right? Okay, IPC set. So this will set the three fields that is pointed to by the buff in the SHMID data structure. okay, associated with this particular shared memory segment. And the what are the three members? What are the three members? That is nothing but permission UID, permission of group ID, and permission of mode. Okay, so this is basically used to set the permission for the shared memory that is pointed by the buffer. Okay, then next one RMID is used to remove the shared memory segment from the memory. So this is used to destroy the shared memory segment. Okay, and these are the three um, functions commands that are specified in Unix single Unix specification, and the rest two, these two are something that is added provided that is provided by Linux and Solaris, but it is not part of the single Unix specification. Okay, so this is available in Linux and Solaris operating system. SHM lock, okay, which is used to lock the shared memory segment in the memory, and SHM unlock, obviously it is used to unlock the shared memory segment in the memory. Okay, so this is about SHM control function. Okay, okay, now we know how the shared memory is created by using SHM get function, and how the various operations on shared memory can be done by using SHM CTL function. But still the shared memory what has been created is not part of the process, right? Part of the address space of the process, and it can be attached to the address space of the process by calling the function SHM-AT. AT stands for attach. Now let us see um, the syntax of this. Yeah, so this is how SHM function will be called with the following parameters. Okay, obviously I have to specify the ID of the shared memory that need to be attached, right? Okay, and this can take various values, and let us discuss about this address and flag later. Okay, yeah, and on successful it will return a pointer to the shared memory segment and -1 on error. Okay, so what do you mean by attachment? See, we all know, we have learned this in our operating system. Process will be having some structure, right? Okay, so it will be having its own address. So this will be the high address, and this will be the low address. So this is where the in the memory the process is the starting point of the, or the starting address of the process. Okay, yeah, and the lowest segment is for the text, and this is for initialized data. Let me write it as iData, initialized data, and on top we have uninitialized data. So something that we have already learnt in operating system. Okay, yeah, and what is the next one? Next one we have heap, isn't it? Which grows in upward direction. So this is for dynamic memory allocation and all those things, right? And on top I have stack. So this is for the recursive function for all those things, right? Where the value need to be stored, and this grows in downward direction. Okay, now the shared memory that has been created, let me write as yeah, shared memory SM, that has been created using SHM get function. It is still not part of the address space of the process. Let me name this as P1. So it is still not part of it, right? So to make it as a part of the address space of this process, I have to make use of SHM AT function by the calling process. Okay, so the call, if the P1 calls this function, then I should be able to attach this shared memory in the address space of this calling function. Okay, so after successful of SHM AT function, so this SM, okay, this will be part of the address space of the process P1, and it is placed in between heap and stack. Okay, so this will be the um, shared memory that is residing inside the memory address of the process, calling process. Okay, yeah. So this is the pointer to the shared memory segment that will be returned on successful SHM-80 function. Okay, now where I have to attach, that is defined by, so obviously how will I know on what point this shared memory need to be attached, right? So that is defined using this address. Okay, this will take various possible values, and if the address is 0, okay, the segment is attached at the first available address selected by the kernel. So this is selected by the kernel for this particular process. Okay, and this is what is preferable. We should always give the value as 0. 0 is something that is preferable, and we call it as a recommended technique. Okay, what if the address is non-zero? Okay, so if the address is non-zero, then it depends on another flag value, whether it is specified or not. Okay, SHM R&D stands for round, and as the name suggests, this is used for rounding up the address space. If it is not specified and if the address is non-zero, then the segment is attached at the address given by the ADDR. Okay, so it will be attached at the address that is specified as a second parameter here, right? Okay, now let us see the third possible value. If the address is non-zero and this flag, if it is specified, then the segment is attached at the address given by address minus the address modulus SHM-LBA. SHM-LBA is nothing but low boundary address multiple. Okay, and it is always a power of 2. And what the arithmetic does is it rounds the address down to the next multiple of SHM-LBA. So these are the possible values of address we can have. Okay, so if it 0 is the recommended one, where the kernel selects the address where the shared memory need to be attached, and the other two, if it is a non-zero, then it is dependent on the flag value, whether it is set or not. Okay, so this is about address space. Now, yeah, coming to the last one, this flag. Yeah, and which is recommended? Of course, the first one. Okay, yeah, unless we plan to run the application only on a single type of hardware, which is highly unlikely in today's scenario, we should not specify the address where the segment is to be attached. Okay, so these two shouldn't be specified unless we want to run it on a single type of hardware, which is not the case. So this is always the recommended one. Okay. Yeah, and the value returned by SHM-80 is the address at which the segment is attached, and -1 is sent on error. Okay, so this is about SHM-80 function. Okay, so this is used to attach the shared memory that has been created previously to the address space of the calling function. Yeah, I forgot to mention about the flag. So the only flag that is that need to be specified is SHM read only. Okay, RDONLY. Okay, so what can be the operation based on this flag? See, if this flag is set, then the segment is attached read only. Okay, otherwise if it is not set, then the segment is attached read write with the read write permission. Okay, so this is about the flag. Okay, now coming to the last one, SHM DT function. This is, by now you might have already figured out what DT stands for. So using SHM-80 function, we have attached the shared memory into the address space of the process that called it, right? Now, after using the shared memory as a tool for inter-process communication, it has to be detached from the address space, right? So that is done by using the SHM-DT function. Okay, so as the name suggests, this stands for detach. DT stands for detach, and the syntax is this. Okay, yeah, and it will return a 0 value on successful and -1 on error. Okay, and what are the parameters that are passed? We have only one parameter that is passed. Okay, which is nothing but the address. Okay, now what address I have to pass here? So this is nothing but the address, that is the value that is returned by SHM80 function. So if you observe, yeah, um, the SHM, you might have observed the SHM80 function will get the return address value, right? So that need to be specified as a parameter to SHM-DT function. So from this address space, the shared memory that has been attached will be removed, or it will be detached from the uh, processes address space. Okay, so this is about SHM-DT function. And yeah, I'll rectify one confusion what you might have encountered. See, SHM-DT function will only remove the shared memory from the address space, okay, and it will not destroy it. So to destroy that, I have to make use of SHM-CTL function with the command IPC RMID, right? So this is used to completely remove the shared memory from the system. Okay, and this function is only used to remove it from the address space of the process that has called SHM80 function previously. Okay, so this is about the various functions associated with shared memory.
The last topic for module 4 is client server properties. In this, we will detail about some of the properties of the client and server that are affected by using the various IPC methods. So when I talk about various methods, I am talking about the topics what we have seen in this module 4. That is pipes, FIFO, then the three system 5 IPC mechanisms, that is a message queue, then semaphores, and finally shared memory. Now let us consider the simplest one, client server relationship by making use of pipes. Okay, so what structure we have is a simple one. I have a client, then we have a server, and the communication takes place by using two half duplexed pipe. The concept what we have already seen in pipes, right? This diagram is very familiar in the concept of co-process, isn't it? Yes. So this using these two duplexed pipeline, the client will be able to, the client acts as a parent, so it forks and exceeds the desired server, which happens to be the child. Okay, and this kind of arrangement, it is called as open server arrangement. Okay, because we have a open server, we can build an open server like this, right? And this server opens files for the clients instead of the client calling the open function. And we assume that the server is the set user id function, set user id program, giving it some additional permissions. So the server uses the real user id of the client to determine whether to give it the access to the requested file or not. So this way we can build a server that allows certain users permission that they don't normally have. Okay. The server, yeah, which is the child, can pass back the content of the file to the parent after verifying whether the client is having the permission to access the desired resource or not. Okay, so this is about the simplest client and server relationship by making use of pipes. Okay, so there are many advantages also, but with these advantages there are some limitations also. See, this works fine for regular files, and the problem is it can't be used for special devices files. With respect to FIFO, we have seen the example of client server previously. This diagram is something what we have already know of, right? And see, if the client is if multiple clients are communicating to server, that is one-way communication where the client is sending only data, then one FIFO is required, right? Well-known FIFO. The name well known because the path to this FIFO is known to all the clients. That is the assumption. So it is called as well-known FIFO. So this is when this is the structure when a client only want to send data, and if the server want to reply back, then what it has to do, it has to create a client specific FIFO and write individual reply to this client specific FIFO from which the client reads the reply, right? Okay, so something what we have already seen, client server communication using a FIFO. Okay, now let us consider the other mechanisms. And of course, this cannot be such kind of architecture or client server structure cannot be implemented by using pipes, because as we all know, pipes does not have a name, right? So we need some named IPC mechanisms, maybe a message queue or a FIFO or other IPC mechanisms like semaphores and shared memory. Yeah, client server properties. Let us look into the properties with respect to the possibilities with the message queues. So there are two possibilities what I can have of client server arrangement by using a message queue. That is the first one is a single queue. A single queue can be used between the server and all client using the type field of each message to indicate the message recipient. Okay. So when I talk about recipient, it can be either a client or the server, and each message is contains something called as a type field, right? Something what we have already learned in message queues in our previous lecture videos. So using this type field, um, each sender can point out or identify the recipient of the message. Okay, so yeah, let us have one scenario. I have multiple clients and there is a single queue and there is a server. Okay, so using the and this common queue is used for communication between all the clients and server. And see, suppose C1 client 1 want to communicate with the server. So what it will do, it has to send a request, right? Suppose in the request in the sense it has to send a message. So in the type field it will specify the type as 1. Okay, type field it will uh, mention the value as 1, and in the request it will also send its PID. Okay, let us assume it to be some 100. Okay, so this is sent to the queue. Now this queue is accessible by the server will read whatever the client has C1 has sent. Okay, so it will come to know the PID of the client because that is also mentioned in the request, and after reading this the server will send a reply back to the same queue, right? It will send back to the same queue, but with the type field should not be 1, but the type field now should be the process ID of the client that has requested some service, right? So with which uh, the client will come to know, yes, this response belongs to me, right? So this message that has a type field of 120 will be kept in the queue, and this client will come to know that yes, since 120 is the PID of itself, it will come to know that this response belong to itself. So using this single queue, multiple clients and server can communicate. So which was not possible with respect to FIFO, isn't it? Because there was a lot of ambiguity with respect to which response belong to which clients. So client specific FIFO had to be created, but it need not be the case with respect to message queue, where a single queue can be used as a communication between multiple clients and server. Okay, that is by using the type field of the message. Yeah, then the other structure is individual message queue can also be used for each client. Okay, so this is the other possibility. So here what do we have is each and every client can have its own queue. Okay, its own queue. So it will create its own queue. So this, let me name it as C1 queue, which is created by the client C1, okay, using the private key. Okay, so each and every client will be having its own queue. And there's a server. Okay, and server is also having its own queue. So this let us name it as well-known queue. Yeah, as the name suggests, well-known queue. This is known to all the clients. So this queue, which is created by the server, is known to all the clients. Okay. Yeah. Now let us understand how exactly the client will communicate with the server or send a request to the server. See, obviously, the client's individual queue is not known to the server, but the server's queue is known to all the clients. Okay, the client will send a request to the server through the well-known queue. So the request is sent, and request is sent in terms of a message, right? And the message type will include, or this message will also include, the ID of the client's queue. Okay, so it is C1, isn't it? So this ID of the message queue of the client is also mentioned in the request. Okay, now the server will read this, whatever the client had sent, and it will come to know the client specific queue ID, right? So based on the ID, message queue ID by the client that is specified in the request, it will come to know it's it will understand where to send the response, isn't it? So response is sent to the client's individual queue, and through this the client can read the responses. So this is how client and server can also communicate by having a multiple queues. Okay, yeah. But again, this is not so one. There's a major problem with this technique. That is, each client specific queue usually has a single message on it, right? Either a request for the server or the response for a client. So this seems to be wasteful of a limited system-wide resource. So instead of that, we can use FIFO only, isn't it? We can use a FIFO because we all know that this is much more costlier. Using a message queue is much more costlier than using a FIFO. So this is the major problem with respect to the second technique, that is having an individual message queue for each and every client. But we can rather go with the first one, where a single queue can be used for multiple client server communication.